This is the lab on Planck's constant, and I have revised this in the meantime. This is the old document. I don't have access to the new one because of getting back and forth to my office, and today I'm able to. So anyway, short story long, here's part of the theory. This is just for the LED experiment. In the meantime, I added also a theory for the photoelectric effect. Now the LED experiment actually will do that, and this is the setup that I used. I used almost the exact same setup as you see here, and then interestingly I made a mistake at first. I'm trying to figure out this is actually where the LED is that should be measured eventually, and I put that LED in just for checking. Turns out it's actually in the way, even though it's parallel to the other one. It actually took voltage away from the other one. I have to figure out why that is. In any case, I took it out and was able to proceed, and you will see how that worked out. These here are actually the data, and so all I did is I measured the voltage here and then have Excel help you with figuring out what Planck's constant is with the formula. I mean, you could do it yourself, respectively the average and the Planck's constant from the slope that Excel is going to tell you. There will be a second table for the photoelectric effect. As I said, this is the old document. I don't have it here, and I'm going to show you now how the experiment works with the LED. I already have it, and then I still have to record the one for the photoelectric effect. All right, let's get going. Okay, so this is the lab on Planck's constant. Here's the setup. So I'm going to put the first LED on here, and I'm going to decrease the resistor right before that, the potentiometer, and there it turns on. Here it's at maximum brightness. I think that what can be seen, but I'm looking for when it just turns on, and boy, it's right there, I want to say. Okay. I don't think that actually shows on the video. Okay, that one is 1.46 volts when it turns on. Okay, turn that one up here, the resistor. I can keep the switch on. So this was the red one, obviously. Alright, so again, turn the resistance down, and we can see that's actually the amber one, and that should show up in the video. At least I hope so. And again, I'm going to look for it when it just turns on. So around here. I mean, I can see a faint glimmer there. Okay, 1.57 is when it does that. Alright, next one. This one here I have to switch, and ooh, I didn't pay attention to if I turn this LED the right way, so I'll find out here. Let's see. Yeah, actually I did. Okay, so this is the yellow one, obviously. Alright, and then it just turns on, just that little glimmer there. Here I can see it, just a tiny bit. So 1.62, that's relatively close. That makes sense because the wavelengths between 600 and 590 are really close, of course. Notice that the color was quite a bit different. You know, between amber and yellow. Okay, so this one here is the green one, obviously. And again, for just when it turns on. And usually this is done by cusping this with your hand. And yeah, I know when it turns on, it doesn't show on film. It's just too faint. And the room I'm in is not the darkest, so this one is 1.68, and
the last one. And obviously that one is blue. Alright, try to get this down as much as I can. So that just turns on. Kind of here. Again, very faint. 2.32. And that's actually all that had to be done, of course, plus the setup here for Planck's constant using LEDs.
All right, so here's the applet for the photoelectric effect. So I didn't do the experiment there. This is the applet at PhDT, Physics Educational Technology, for the photoelectric effect. So this is where you would have to take the measurements. I'm just going to show you how to take them. First of all, there are 3 sliders here. One of them is the wavelength. So here, for example, I put it somewhere in the red here. This would be a red wavelength. I increase the intensity. There's a second slider. Let's say I make it about 20% or so, somewhere around there, right? And it shines on the electrode over here. And now I'm going to introduce a negative voltage, like negative 1.4 volts. So that means it's negative in this direction here. So we have negative over here. Electrons are being kicked out. Actually not. We don't see any, right? But let's say that they would be kicked out. Then they would have a certain amount of kinetic energy. But since they're negative, they would be actually repelled by the cathode on the other side. So no current would be flowing, which is exactly what we see. 0 amps is what we see. So this is the main idea before the photoelectric effect. Increase the intensity. That means put more energy into it at a certain wavelength, for example, and you will knock out electrons, and nothing happens. And that's what puzzled physicists. Why is that? So they tried another thing. They tried to increase the wavelength. So here we're in the yellow and the green, and then the blue, and now electrons are actually being kicked out. Now we can actually increase the intensity, but apparently even so they don't have enough kinetic energy to reach to the other side. So I can decrease the wavelength, which increases the frequency, which increases the energy of the light. And that was puzzling. Of course, physicists didn't see these little particles there, right? That's already the conclusion to that the wave phenomenon of that, what light is, should predict increase the intensity, more energy. Well, that's true, but that just didn't work. The only thing that worked was decrease the wavelength, which increases the frequency, and now electrons actually came out. Oh yeah, by the way, these are electrons coming out, not light. The light is here. And the only way this works is that if the light coming in, the photons coming in, is a photon itself, is a particle itself. So here is a contradiction to the wave theory for light. It's the particle theory for light. So which one is right? Physicists soon noticed back in 1905, a little later, maybe in the 19-teens or 20s, because they were busy with World War I in the 19-teens, obviously, that, wow, we cannot decide. Some experiments, light definitely is a wave, and some other experiments, light definitely is a particle. And again, we're actually looking at the electrons as particles here. They don't actually show the photons as particles. That's this beam here. That would be it. Okay, decrease the wavelength, increase the frequency, and now electrons actually could go over there. Notice actually the current had already increased before they even went to the cathode. It's kind of like a little strange on this one here. Okay, anyway, I'm going to show you what you should actually measure. So you see down here the negative voltages that are here. Actually consider them as positive numbers when you plot them. And what I'd like you to do is you start at 6 volts, and then you go 5, 4, 3, 2, and you know, like 5. And if you don't get exactly to 4, because it's just the slider is a little bit clunky here, you know, just do 3.8, you know. But usually you actually will be able to achieve it. So start with 6, and then what you're going to do is you start in the large ultraviolet. By the way, the intensity is actually 100% here. So in the large ultraviolet, you get really high energetic photons from the beam here. They're knocking out the electrons from the anode here. They need some energy to actually get them out of the material. It's called the work function. And all the surviving energy then would be the kinetic energy, which is what you see. These electrons are going really fast. And then decrease the frequency, which means you increase the wavelength. And notice at some point, actually, you reach the zero current here. So if this was a measurement, then you would measure this one here for sodium. You can see that up here. At 6 volts, the cutoff frequency is 149 nanometers. You only choose one element. Could be sodium, could be zinc, copper, platinum, calcium. This question mark thing here, I already did that as an example in Excel. I couldn't figure out which one that actually is because its work function didn't match any others. So you can choose any one of the 5 that are named here, and then measure for each voltage, you measure the wavelength, and then with Excel that actually calculates it into the frequency and the energy, and then the slope of the line, which is hopefully close to Planck's constant, which then validates the idea that the light that is coming in is actually photons, and for this particular experiment, it is particles, not waves. For another one, like refraction, it would be, or polarization, it would be actually waves, because that's the only way that polarization and refraction work. Diffraction, the same thing. All right, and that's actually it for the experiment.